Welcome to Calculus, AP Calculus 7.3, Integration by Parts, also known as UDV substitution. Now, just got done dealing with some substitution, but that was UDU substitution, but both of these are useful if we have a function of x times another, times another function of x dx. UDV substitution will work more on real-world problems, because in UDU substitution, we'd have to take the derivative of say g, called GU, take the derivative of it, and hopefully it would take care of some of f. So they have to be kind of cooperative functions. UDV, different variables, we may be able to do things there that we couldn't do with UDU substitution. Now, here's the deal. It comes down to which one do I want to be U? Do I want like f of x to be U and then this to be dv g of x? If we think about it, in our formula we're going to need a plain old U. Well, if f of x is U, I've got U. I'm going to need a plain old v, which means I'm going to have to be able to integrate g of x dx. So if I have a function that's not easily integrable, I would probably not like to have it be my dv term. Well, x, I can integrate it. Sine, I can integrate it. I'm just going to give this a shot, but I'm going to be willing to erase and come back. I'm going to have, I don't know why I did that. I'm going to have u be x. And then next to it, I'm always going to set this up the same way, dv has to be the rest. dv must be sine of x dx. Notice if there's a d on the left, there's a d on the right. So what do I need? I still need du, so the derivative of u is the derivative of x. I still need plain old v. In fact, I need plain old v twice. To get to v from dv, I have to integrate sine of x. So v I'm going to put under here. It wants to be cosine. However, the derivative of cosine is negative sine if I work backwards, so this needs to be the opposite of cosine. Once I have those in place, my integral, so now this becomes integral UDV is equal to, if I set it up this way every time, u here, get that blue pen out of here, u here, dv there, du here, v there, it's these two together, so it's x times negative cosine, or negative x cosine of x, minus the integral of, take a look, it's v and du, it's these two together, so that would be negative cosine of x with dx. All right, I think I can handle that. I'm going to pull a negative out of here, so this is equal to negative x cosine of x plus, and the antiderivative of cosine wants to be sine. Let's check that in reverse. The derivative of sine is cosine. Again, the negatives have taken care of each other, plus c. That is what y is equal to, or that's what our integral is equal to. Should just leave it at that. The integral is equal to, not y. I'm thinking of the next page of problems. So there we have it. Okay, now I'm going to just use kind of a sidebar area up here. Let's say we just kind of went into this without a whole lot of thought. And I said, all right, let's let u be y and dv be ln y. The derivative of u, this is easy, looks just like the last one. du is dy. And v is, there's a dy here as well, ln y dy. V is the antiderivative of ln y. I don't know what the antiderivative of ln y is. There's nothing I take the derivative of that gives me ln, and you might say, well, what about 1 on y? No, ln y's derivative is 1 on y. 1 on y's derivative is not ln y. So I don't know. Therefore, I would erase and I would say, okay, I guess I'm going to try u is ln y and let v be y dy. So hopefully I'd be alert to that at the beginning. I don't want to have to integrate ln y. Therefore, I don't want ln y to be my v decision, be part of v. So du, I can do that. That's 1 on y dy. And integrate y, that's a breeze. V is y squared on 2. So, sorry, sliding this thing all over the place. So what do I get? I get my integral equals uv, again, diagonal, uv, that's y squared on 2 ln y minus the integral of, I'm going to put the 1 on y here, I'm going to save the dy for last, the y squared on 2 there, and the dy last. This times this times this. So a little algebra cleaning. Y squared on 2 ln y minus a y cancels a y. I just get y on 2. In fact, I'm going to make that y here 1/2 outside dy. So I end up with, let's see, y squared on 2 ln y minus, I'm going to need one more line, y 1 on 2 times integral y squared on 2 plus c, or finally, should have written a little smaller, y squared on 2 minus y squared on 4, oh, ln y, I know you saw that, y squared on 2 ln y minus y squared on 4 plus c. And we have it. Okay, let's take a look at problem C. Can I integrate 3t? Sure I can. Can I get the derivative of 3t? Sure I can. Can I integrate, get the derivative of e to the 2t? It's very possible I could do this either way. If I have an option, and you'll see why shortly when we get to d, or actually when we get to e, if I have an option and one of my terms is polynomic, I'm going to choose it to be u. So I'm going to have u be 3t, dv is going to be e to the 2t dt, d on the left, d on the right, du is 3 dt, and v is the integral of e to the 2t. I don't know why I didn't put that over here. E to the 2t, it comes from e to the 2t, but the derivative of e to the 2t is e to the 2t times 2. I don't want times 2, divided by 2. So we get this times this, diagonal. I get 3t times e to the 2t on 2, I'm going to make that 3/2, minus the integral of those guys. So that is 3 on 2, in fact I'm going to put that out front, 3 on 2 e to the 2t dt. 3/2 t e to the 2t minus 3/2 times, what's the integral of e to the 2t? We already did it. E to the 2t on 2 plus c, for a final answer 3 on 2 t to the e 2t minus 3 on 4 e to the 2t plus c. Back of the book might cancel, might factor out some fraction, might factor out the e to the 2t. We should be able to work through that algebra to match. Okay, so worth doing this. Can I take the derivative of this? Yes. Can I take the derivative of this? Yes. No preference. Can I take the integral of this? Yes. Can I take the integral of this? Yes. No preference except my polynomial rule. My polynomial rule says it's better to choose polynomial if you have a choice. If we can integrate the other thing is basically what it comes down to. And I can integrate cosine and integrate that integral of cosine all day. So we get u is x squared. We get dv then would be cosine of x dx. Derivative of u is 2x dx. And plain old v, well, the integral of cosine wants to be sine. Does that do it for me? Well, the derivative of sine is cosine, so we're good. So here's what we get for starters. Let's see where we're heading with this one. I want u times v, so I have an x squared sine of x. looks good, minus this. I've got a 2, I've got an x, I've got a sine of x, and I've got a dx. And now all I have to do is find the integral of this, and I can't find the integral of that directly. Can I u du substitute? Well, if u is 2x, the derivative of that's 2 doesn't pick up the sine. If u is sine, the derivative of that's cosine. I have no accounting for the cosine, so I'm going to u dv again. I'm going to go u is 2x. dv is sine of x dx. du is 2. Plain old v wants to be cosine of x, but the derivative of cosine is negative sine, so negative cosine. And now I have patient little x squared sine of x waiting around for that integral. And that integral is the diagonal. I've got a negative, I've got a 2, I've got an x, I've got a cosine of x. I need a dx here, darn it. And I need the integral of this guy. So that's minus the integral of, I've got a negative, I've got a 2, I've got a cosine of x, I've got a dx. And now I'm in business because I can find that integral right here. Okay, what do we end up with? X squared sine of x minus minus plus 2x cosine of x. Careful here, I got a minus, that's plus, but I got another minus. That is plus, or that's minus, excuse me. That's minus 2. The integral of cosine is sine. The derivative of sine is positive cosine, got it. Plus c, and there we have it. Wow, that's a lot going on. Now, I want you to imagine just for a moment, what if this was x to the 4th instead of x to the 2nd? At this point, I'd have an x cubed. That would be causing a problem. I'd do this again. At this point, I'd have an x squared in here. That would still cause a problem. I'd have to do this chain link again. And then I'd have another x, and I'd have to do it again, and we'd do it over and over and over. And fortunately for us, there is what's called a tabular method, and I'm going to grab my book here and pull that up so we can take a look at it. Tabular integration. So we have seen that integrals of the form a function times a function. We can do those sometimes with u du. We can do those sometimes with v dv. But in which f can be differentiated, I can take the derivative until it becomes 0. Well, what does that really mean? The derivative of what is 0? The derivative of a constant is 0. So before it became a constant, if we were taking derivatives along the way, let's say the constant 7, the derivative of 7 is 0. Well, what's the antiderivative of 7? 7x. What's the antiderivative of that? We're going to get x squareds and x cubes. They're pretty much saying if one of the functions is a polynomial, and g can be integrated repeatedly. Repeated integration of g. We just saw a problem where we integrated g once but couldn't integrate it a second time after that, not conveniently. If it can be done without difficulty, we have this method that's tabular. However, if many repetitions are required, like I just said, the calculations can be cumbersome. In situations like this, there's a way to organize the calculations that saves a great deal of work. Not only saving, we don't want things just to be faster, it's safer. It's called tabular integration, and it's shown here. So here we go. X squared can be repeatedly differentiated to be 0. So basically, I'm choosing it to be my u, and I'm differentiating it down to 0. E to the x can very simply be repeatedly integrated. E to the x, e to the x, e to the x, e to the x. And then they say what we do is we take this x squared times the integral of that. That is exactly what we just did. That is u dv substitution. So our solution becomes x squared e to the x, then minus 2x e to the x, then plus 2 times e to the x. And that's our solution. We've done all the work, and this just organizes. Want to see another example? Let's take a look at this one. A little bit more going on because of the x cubed. But because sine of x Sine of x, the integral is going to become something about cosine, and the integral about that's going to be positive or negative sine, and then back to cosine, sine. I could integrate that all day, just got to be careful with the negatives. X cubed differentiates to 0 eventually, and here it is. X cubed, 3x squared, 6x, 6, and 0. That 0 just tells us basically where we will stop with this. So basically, x cubed is our u, sine of x dx is our dv. The derivative, or the integral of sine, negative cosine, integral of that, negative sine, back to cosine, sine, you can check it. So our final solution, as you can see, wow, is that nice compared to what we just did, is the positive version of this product. Well, that's going to be negative x cubed cosine. Got it. The negative version of this product, well, that's going to be positive 3x squared sine x. The positive version of this plus 6x cosine, and the negative version of this minus 6 sine plus the constant coefficient. That is pretty slick, but again, two conditions have to be satisfied. One of our functions has to be able to be derived to 0. The other has to be relatively easily integrable repeatedly. And this one most certainly is. The last one, e to the x, is our favorite friend on this. Okay, so with that, let's try this problem. A function of x, a function of x. Is this, can I take this derivative down to 0? Yes. So basically my u is being chosen to be 3x squared, and the first derivative of that is 6x, and the second derivative of that is 6, and the third derivative of that is 0. Basically, my dv is going to be e to the 2x. Now, it's going to be dx on there, but I'm not going to write the dx down. So, the first integral of e to the 2x, well, it wants to be e to the 2x, but e to the 2x's derivative is e to the 2x times 2. I don't want times 2. The next integral, well, it's going to be 1/2 times this guy. I just pull the 1/2 out and integrate this again, so it's going to be e to the 2x on 4. This likewise is going to be e to the 2x on 8. You can check that. So our answer is, if I go ahead and do this, it's going to be this to this, the positive version of that, the negative version of that, and the positive version of this. How neat is this? I got a 3 times a half. 3 halves. I've got an x squared, and I've got an e to the 2x. I've got a minus, it's all minus. I've got a 6 on 4, that's 3 halves. I've got an x, I've got an e to the 2x. And this times this is going to be plus. I've got a 6 on 8, 3/4. I've got an e to the 2x. And I've got a plus c for our solution to this integral. Wow, that had an extra chain in it, and compared to this problem, truthfully, probably not just easier because we had more steps here, but just maybe a little bit easier to work with. So not too bad at all. Really nice way to handle that. I guess they're both just squared, so we kind of had the same number of steps, but a really, really slick approach to this. Okay, I think I'm going to continue this. I've got some time. Let's jump to the next page. Solve the initial value problem. So this is basically saying we want this to become y equals. Let's zoom in here just a little bit on this. So to solve this initial value problem, I want to get y. To get y, I want dy. So I am really taking this dx over to the other side, multiplying both sides by dx, and the integral would be y, or the solution would be y equals the integral of x plus 2 sine of x dx. Is that a candidate for tab? Well, this would derivate down to 0. This is easily integrable, so we could do this with tab. I'm not going to, because in one step I'm down to a constant, but you could. So I'm going to, since I can easily find the integral of this, I'm going to choose the polynomial for my u value. U is x plus 2. That makes dv the rest of this. That would be sine of x dx. Derivative of u is 1 dx. And the integral of sine, v, wants to be cosine, but cosine's derivative is negative sine. So v is negative cosine x. All right. What do? We go equals this times this. Careful, it's all of x plus 2 times negative. I'm going to put that out front. Cosine of x minus the integral of those guys. Negative cosine x dx. Pull the negative 1 out, plus positive. We've got y equals negative x plus 2 cosine of x. The antiderivative of cosine wants to be sine. Let's check it. Derivative of sine is cosine. That's good. So plus c. That's the coefficient. At this point, we're going to say y is 2 when x is 0. So this is negative 2. 2 equals negative 2. Cosine of 0 is 1. Sine of 0 is 0. So c is 4, giving me a final answer of y equals negative x plus 2 cosine x plus sine x plus c, but c is 4. All right. Okay, let's take a look. We got to be willing to perhaps erase, go back, change u's, dv's. Again, we'd be multiplying this dx across, so we end up with, I'm going to take this u and change it to y. That's a little bit troublesome for me for right now. We may deal with that a little bit later, but that u and the u I'm going to substitute with, I'm getting comfortable with that u right now, so I'm just going to talk about those being terms of y. So I would get y equals the integral x secant squared of x dx. U du will not help me. If I make this u, du is tangent x. Not such a good thing. Now, u dv might. Is this integrable? Derivative of secant squared is not tangent. The antiderivative of secant squared is tangent. Antiderivative, which means I really want this to be my dv and antiderivate. So I'm going to have u be x. Let's see how this works out. We may change our mind. dv is secant squared x dx. du is just dx. v is the antiderivative of secant squared, tangent x. All right. I see a little bit of challenge in our future here. Let's see what happens here. I take u times v. This equals, let me give myself some room here. That's x tangent x minus integral, this with this, tangent of x dx. I don't have a direct path integral to tangent. Maybe we're going to learn one right here. But maybe I can handle this with trig identity, sine of x on cosine of x. Now, if you've been paying attention the last few days in class, I have said if we get a sine on cosine, that's a u du, and we want u to be the denominator. If we get a function of sine on a function of cosine, we want u to be the denominator. If it's cosine on sine, u is going to be sine, but in this case, u is going to be cosine of x. That makes du, I'm not doing a dv here, du is the derivative of cosine, which is negative sine, but I might rather that be plain old sine since I have plain old sine here, so I'm going to go sine of x is negative du. So I'm going to jump up here. What do we have so far? Patient x tangent x, this is still y equals, patient x tangent x minus integral, what do I have? I have 1 on u. du takes care of sine of x, and there should be a dx, d on the left, d on the right. So negative du takes care of that for me. So y is x tangent x. I'm going to pull this negative out, plus 1 on u. The antiderivative of 1 on u is ln. ln of u, but what is u? U is cosine, absolute value cosine of x plus c. Well, let's fill in some values. Man, it's easy to stop right there. We're used to stopping there, but y is 1 when x is 0. 0 tangent 0 plus ln cosine 0 plus c. Tangent of 0 is 0 times 0. It doesn't get to be more 0 than that. Cosine of 0 is 1. ln of 1 is 0. So I get 1 equals c. So we end up with, final answer, finally, y is x tangent x minus, where am I here? Back it up. It's not minus, it's plus ln, absolute value cosine of x, plus c. However, I changed y, so maybe at the end I'll come back in and turn those into u's. Okay. All right, one more here. If I try u du and I make u be x minus 1, the derivative of that's just 1. That doesn't take care of this x. If I make this be u, the derivative of that's 1. That doesn't take care of this. So this is not a u du opportunity for me. I'm going to give this a shot, and maybe I'm going to come back and try something different. So I'm going to go u is x. Maybe I'll regret that. That makes dv be x minus 1 to the 1/2 square root of x dx. Might regret this. We'll see. The derivative of u, du, is just dx. dv, the integral of this would be, wants to be x minus 1 to the 3/2 on 3/2, but on 3/2 is the same as times 2/3, and we're going to check that. All right, derivative, 2/3 times 3/2 is 1. X minus 1, reduce this. We've got it. So I think we're in business here, but we may still have a little bit of work ahead of us. So we get y equals product of these. Okay, I've got a 2/3. I've got an x. I've got an x minus 1 to the 3/2. And the nice thing about that, I don't have to do anything with it. It's outside the integral. Minus the integral of these. 2/3 I'll put in front. X minus 1 to the 3/2 and a dx. And I can integrate that. So we're in business. Y equals 2/3 x times x minus 1 to the 3/2 minus 2/3 times x minus 1 to the power rule, increase it by 1, x minus 1 to the 5/2 divided by 5/2, flip it, times 2/5 plus c. So y equals 2/3 x, not absolute, quantity x minus 1 to 3/2 minus 4/15 x minus 1 to the 5/2 plus c. Are we done? Nope. And wow, how merciful of them to give us x is 1. Because when x is 1, I get 2/3 times 1 times 0, and I get a 0, and I get c is just equal to 2. So final answer, y is 2/3 x times x minus 1 to the 3/2 minus 4/15 times x minus 1 to the 5/2 plus c, but c is 2. And there we have it. We've got perhaps a little bit more to look at, but at this point right here, I'm fatigued, maybe you're fatigued. We're probably in pretty good shape to continue on those. I will wrap those up in another video. Thanks for tuning in. If you're looking for your problem set, There it is.